Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. I'm here with another lecture about the epoxide. I want to practice some more example about nomenclature of epoxide, and after that one we will practice some method about how to prepare them. Okay, the compound that we have is a cyclic, and I'm going to try to start labeling it. I will start from here, 1, because I have oxygen and also the methyl there, so it's better to put 1 there, and that's going to be 2 here. We have 6 carbon, so this is going to be cyclohexane. And the way we're going to name it, we will say between 1 and 2, we have epoxy. Epoxy will get priority over methyl, so 1 and 2 epoxy. And then on the first carbon, we have methyl, so we say 1 methyl. Next, we do have a ring, and the ring is made of 6 carbons. So it will be cyclohexane. I go cyclohexane. Now, do we have stereocenters? Yes, we have 2 of them, and those are the stereocenters. Let's find the configuration for them. I go here, 1, where is 2? This is going to be 2, and 3, it will be here, and that's going to be the 4th priority. So this one, it will be clockwise, and the carbon number 1, it will be R. So carbon number 1 got R configuration. How about carbon number 2? Carbon number 2, this is the carbon number 2. So we have 1 here, the 2, it will be there. This is going to be 3, and hydrogen, it will be the 4th priority, and hydrogen or the 4th priority is back. So this one is going to have S configuration. And I'm going to say this has S configuration. Okay, now that I know I have R and S configuration, I need to show them in where they are. On the first carbon, I have R configuration, and the second carbon, I have S configuration. So the correct name, it will be 1 R, 2 S, 1 and 2 epoxy, -1 methyl cyclohexane. Okay, now we have a compound that still it has oxygen bridging between 2 carbons, but the 2 carbons are not connected to each other. The common name for this organic solvent is THF, or tetrahydrofuran. And how do we name this one? We have like a ring that's made of 4 carbons, and there is oxygen bridging between those 2 carbons. And so I go 1, 2, 3, and 4. Between 1 and 4, I have a bridge, and that's going to be epoxy. Now we have totally 4 carbons, so this one will be 1 and 4 epoxy, butane. Now that we practice enough example about nomenclature, let's go after some chemical reaction and how to prepare them. And the one common method for preparing epoxide is using peroxy. And peroxy, like there is a carbon that it attached to a carbonyl group, and also it has 2 oxygen that they are attached to each other back to back. Whenever you have 2 oxygen attached to each other through a single bond, the correct term for it will be peroxide. And it's acidic. Why acidic? Because we have this H. Okay, we have this H that's attached to oxygen, and oxygen electronegative. So we do have high electronegativity here. So that H is going to have a good positive charge on it. Okay, that's one term and one method. The second method is by using the halohydrins. And so you have a double bond. You add the bromide or chloride in the presence of solvent like water, and it will give you alcohol plus bromide or chloride. And next step, you treat it with you will treat it with a strong base, and the strong base, it will get the bromide out of the system, and we will get epoxide. So final product, it will be epoxide. Okay, I want to practice these 2 methods one by one. Okay, the first method is going to be by using peroxy acid. So I have metachloroperoxy benzoic acid, and this is the abbreviation for it is going to be MCPBA. Now, what's the purpose of M here? Imagine you have a phenol. The first 2 positions that they are close to the functional group, we call them ortho. And next 2 positions, we call them meta. And last one, okay, this one, it will be the para position. And where is the chloride? The chloride is sitting in a meta position. This position is a meta position. And what's the functional group? This is going to be our functional group. So the correct name for it will be metachloroperoxybenzoic acid. Okay, and I have a double bond. I'm going to treat it with peroxy acid. Very soon it's going to put it's going to put the oxygen there, and oxygen, it will be bridged. Now oxygen, it can be added from the top or the bottom of the molecule. Remember, your molecule it has sp2 hybridization. That means it's going to be flat. Okay, at least the double bond section is a flat, and because it's a flat, addition can happen from the top or from the bottom of the molecule. So I can have O on the top or at the bottom of the molecule. And if I add O on the top of the molecule, and then I will get this. Okay, so O was added on the top of the molecule. Another one, I'm going to add O, back of the molecule. So I get this one. Now, I got two stereocenters, and one stereocenter it will be here, and that's going to be the second stereocenter. I should not say two stereocenter. I got two molecules that do have the two molecules that do have stereocenters, and let's check the relationship between them. Okay, the first one, I'm going to say this is going to be 1, and here we get 2. This one, it will be 3. Where is the fourth priority? Here, this is going to be clockwise, and because it's a clockwise, I got R configuration. And the next one, I go, this one is 1. Okay, this is 2, and 3 is here, and that's going to be the fourth one. Again, let's follow the number. It's supposed to be R. Okay, it's supposed to be R because the fourth priority is facing to us. It will be S. So this one is going to be S. What's the relationship between these two? We got enantiomer. We got enantiomers. Is there any preference for one of these enantiomers? Absolutely not. What does it mean? It means we're going to get mixture of enantiomers. So this technically solution, the product, it's going to be racemic. It means optically not active. And in this case, we say the reaction is not enantioselective. So no enantioselectivity, okay? No enantioselectivity. Okay, now I have two compounds, and those two compounds, the only difference between them, position of the technically these two substituents. Let's check those two. And we change position of those two substituents. And so what will happen? In the first one, I have ethyl. Okay, here, that's going to be the first priority. And this one also the first priority. They're on the same side. It will be Z. And here, this one on facing technically into us. And this one, it will be there far from it. So these two, they will be E. And what's the relationship between them? They will be diastereomer. Okay. Now, what will happen if I treat them with peroxy acid? If I add peroxy acid to them, I will have oxygen, okay, there, and also I will get oxygen here. So nothing surprising. And now, because I have two stereocenters, I need to assign those two. And every time we get peroxide, remember this, we get an enantiomer of that compound. And so the first one is Z, gave me a product. It gave me two products technically, and one of them I'm showing it, and I'm going to assign the configuration for each one. So I get 1, 2, 3. Okay, this one it will be R. Okay, and the next one I get okay 1, 2, 3. This one it will be S configuration. Okay, I did not change this one. This one stayed as it is, but the second one I flipped it. So I'm going to say this is going to be R, but the second one it will be flipped, and it will from S it will turn to R again because we change position of hydrogen and isopropyl. Now, what's the relationship between R and S versus R and R? One of the stereocenter stayed as it is. We did not flip it, but the second one used to be S, now is R. Okay, that one is R. Okay, so one of the stereocenter got flipped, while the second stayed as it is. In that case, we say these two are diastereomers. Remember, also, we do have an enantiomer here. Okay, so I started with diastereomers, and I got diastereomers. And in this case, we say we do have a stereospecificity. What does it mean? It means the relationship between the starting point, the starting reactant was kept, and we can see it on the product side as well. They used to be the diastereomers, still, okay? I see epoxide, but they are diastereomers, okay? Still, they are diastereomers. And that's the reason I say we do have a stereospecificity. Okay, the second method for preparing epoxide is treating an halohydrin with a strong base. And the strong base very soon is going to go with after acidic H, and we'll take that one. And now we will get strong nucleophile. So this is going to be a strong nucleophile. A strong nucleophile, it will kick the halide out of the system. And in order to kick it, it has to be in anti position. It has to be. And in this case, as you see, one is up and the second one is down. So they are in a trans position. And then it's possible to kick it out of the system. Why? Because it's a SN2 reaction, and SN2 reaction it will happen from opposite side. Okay, from wherever we have the leaving group from opposite side, and the coming group, it will be added to the system. It will kick the halide out. Okay. Now, what will happen if the bromide, if I put both of them on the same side, like let's say we had a cis and a, isomer, and in that case, because we have a ring and we cannot have rotation inside any ring, and there will be no chance to get epoxide. So if they are on the same side, we're not going to get epoxide. Okay. And again, I'm talking about a cyclic system. And remember, if it's a single bond, always you can have rotation. And this one is a single bond, but still I have a ring, and because it's a ring, I cannot have rotation. Okay. Now we have. We said we can take double bond and treat it with a bromide in the presence of polar solvent, polar protic solvent like water, and that's going to give us a product. And we're going to treat it as product number one, and later we will treat it with a strong base, and the strong base it will take HO from it and it will give us epoxide. So now, what will happen if I add the bromine to a double bond? First step, I'm going to get an intermediate. I will get such an intermediate, and remember, we have a secondary carbon and a tertiary carbon. The tertiary carbon is more capable of handling the positive charge. So what does it mean? It means we get two types of bond. One is a strong bond. This one is stronger. And this bond, it will be weaker bond. The nucleophile, next step, it will tag the tertiary carbon because is attached to bromine, the brominium, through a weaker bond, okay, through a weaker bond. And because we use water as a solvent, and in the next step, water, it will be added to the system. So OH from water will be added to the system, and it will give us, this product. Okay, so OH, it will be added to the tertiary carbon, and a bromide that will be sitting on the secondary carbon. And remember, the addition, it will happen from opposite side, okay? Because this is going to be technically SN2 reaction, and you can treat it as an SN2 reaction. And I'm talking about the second step. Okay, so what's the relationship between the bromide and OH? They will be in anti-position. Okay, now, this is one of the product. The second product, you can put in the brominium at the bottom of the molecule and then add the OH from the top. So you get an enantiomer of it. The OH, it will be on the top, and the bromide will be at the bottom of the molecule. So again, the relationship between them is anti-position. Okay, now I'm going to take one of this, and it will treat it with a strong base. Okay, it doesn't matter which one. Okay, let's take one of them and treat it with a strong base. And so the base is going to go after acidic H, and it will take that one. Then O with a negative charge, it will kick the bromide out of the system. So now that I got O with a negative charge, we will attack technically bromide, and this is going to be an SN2 reaction. And we will have inversion technically there. And so bromide will leave the system, and we get water, and this is going to be the product. So this is going to be one of our product, and the oxygen is sitting on the top, and the bromide left the system, and also we get an enantiomer of this compound. So technically we get two enantiomers. And don't forget that you do have sodium from the starting compound, and also we lost bromide. These two, they will find each other and they will turn to sodium bromide. Okay, so this is the second method of technically preparing epoxide. Okay, I want to actually zoom on two facts. One is the stereospecificity. If you start with cis, okay, cis, you will get an epoxide that it will have those two substituents. They will be in the same site. And we say we will have a stereospecificity. Okay, and if you start with cis, you will get cis. If you start with trans, you will get the trans one. Next thing is, regardless of which method you are using, you are not going to get the specific enantiomers. Okay, you will get technically a mixture of enantiomers. So there is no enantio selectivity, and because there is no enantio selectivity, I get mixture of those two enantiomers, and I'm going to say the mixture will not be optically will not be active. And this is going to be the end of this lecture, and thank you very much.